Swayam Prabha. Digital India. Educated India.
So today we're going to look at hashing, which you're going to see in multiple lectures in this school, today, next week, and and I would think that many of you would have heard this term at least, maybe even implemented it, used some hash tables in Python, Java, or whatever. But we're going to look at it in the language we have been talking about, right? In theory, probability, complexity, and so on and so forth. Okay. So, what is a hash function, right? So, it is a function which takes from a large universe elements and maps it to a small table T. Okay. So, I am going to assume that the size of U is some P. I will tell you in a few minutes why I am calling it P, and size of table is T. I do not know others will use the same notation in the other lectures, but you can do your translation otherwise. Okay. So, first why is this going to be useful in this algorithms for data science? Well, typically when we have some stream of elements and we want to store something about them, right, that has been the theme in small space. Now, if I want to store an element of U, how much space would it take for me? Right, space to store an element of U. Can somebody tell me how many bits do I need to store it? Log? Log P, okay. Log P bits, because P is the size of the universe. So, for example, if I want to represent a number between 0 and 1024, how many bits do I need? 10 bits, right. So, it is log of that size. So, to store an element of U, I need log P bits, and by the same token, if I want to store an element of T, it will be log T bits, and U is going to be, or P is going to be much larger than, right, T. T is a small table and P is my large universe. So, for example, you might think of compiler table or something, and you want to take all words used by your programming language and map it to some 20 cells or something like that. So, T is like 20, whereas U can be very large. Okay. So, it makes a big difference between log P and log T. So, if in the stream of elements I want to store some information about every element, instead of using log P bits, if I somehow do some mapping and store, instead of X I store H of X, I will use only log T bits. So, that is a big advantage. Okay, that is the way we will use it. But what is a big disadvantage? If instead of storing an element of U, if I store its image under H, if I store instead of X, I store H of X. Okay. and I just argued that h of x takes very less space, so that's good. But what is bad? Exactly, right? Multiple elements from U can get mapped to same element necessarily, because P is much larger than T. So, a function which maps this large universe to the small table will not be 1 So, it is going to map a lot of elements into one particular element. So, if you store this, then I will not know whether h of x represents x or y or z. There are many things that get mapped to this h of x. Okay, so that's a disadvantage. Okay, so now we have to be careful. So we want. So now let's talk about what are the good things I want of this h function. Right, I want. Okay. So some features I need of h. Small probability of so there is a word for it, multiple elements get mapped to the same element. Collision, exactly, right. So in the hash function terminology, I want small probability of collisions, right. So that, of course, the tool we are going to use to deal with this is randomization. Okay, that's what we have been seeing, and we will do some probabilistic analysis. So we will, instead of storing x, we will store h of x, and somehow if the h has the nice property that it has small probability of collisions, that's good for me. What else do I need? Well, I want h to be easy to compute. Right, if given an x, I should be able to compute h of x easily. What else do I need? Right. So let me come back to this, the space argument I said. So instead of storing an element, I am going to store h of that element. So let us say this entire stream, somehow whatever I want to compute, instead of storing x, I am going to store h of x. I also need to know h, right, to be able to compute. So in my structure or the solution I am going to have, I have to have h, and every time when an element comes, I can compute it and store h of x. So h also I am going to store it in my structure. So I want the space for h to be small. Right, this small, easy, these are all very subjective terms. We will make things precise as we go along. Okay. So now I am going to think in terms of finding functions which has these nice properties. Okay. Now U is this universe which is coming, I have no control over. Okay, somebody is giving me this user defined data. So now imagine that whatever h I can think of, h will have collisions because h is mapping large set to small set, and an adversary can choose in a way that I say, hey, I have this beautiful nice h function which has all these nice properties. I mean you will come back and say, look at this set, you choose your h, I am going to come with the set where all elements are mapped to same location for this set in h. If that is my user defined set, I am stuck, right. There is no small probability of collision and so on, because worst case, given any h, somebody can come up with the set where all elements get mapped to small number of locations. So there is a huge collision happening, right. And so to defeat against that kind of an adversary, we do, what do we do? That's what we have been doing, right. So let me go back to another analogy, right. Quick sort. Let us say, think of a deterministic quick sort where I say, I choose the first element as the pivot. right? It's a deterministic algorithm, no randomness in the algorithm. Choose the first element of the pivot, do your partitioning and recurse. That's quicksort. Clearly, there are bad input for this, which will result in your n square running time, because adversary can keep a sorted list, and every time your partition really doesn't get you a good split, and it will result in an n square time. So, to deal with that, what did we do? Randomize. So, we said I am not going to pick the first element as the pivot, I am going to pick a random element as the pivot. Now, this random element can be anything, so an adversary does not even know, right. If you know the adversary can come up with the worst case input, no, because by doing this is a very important difference or advantage of randomized algorithms you should know. Building in randomization into the algorithm as opposed to doing an expected analysis of quicksort over all permutations, the randomization is into the algorithm, so there is no fixed input for which this quicksort is bad. Even randomized algorithm is bad, right. Even randomized algorithm, its worst case is n square. But what does it mean by worst case is n square? Worst of what? Right? Randomized algorithm, randomized quicksort algorithm also is n square in the worst case. What does it mean? Worst in what sense? Yeah. Random choices of the pivot. Based on that, so that is something internal to the algorithm for every input. So, there is no input for which it is bad. For every input, there will be choice of pivots for which it is bad. Okay, so that is what makes the randomization built in, so that an adversary cannot play against it and give a worst case input. So, similarly here, whatever hash function I think of and I publicize it, an adversary can come and give me a worst case input and say, hey, on this for this function, this input will map it to one location or few locations. So, there is a lot of collision and you are not saving much. So, we are going to randomize it. So, how do we randomize it? I am going to have a family of functions, family of hash functions, and then I will randomly pick from that family. Okay. So, that is the way we will randomize it. So, we will now talk about a family of functions, right. So, let us call this goes with a lot of names. So, 2 universal, sometimes 2 universal hash family. Right, it's a family. So, this is a family, is going to be a set of functions, not one function, set of functions from u to t with the following property. For all x comma y in u, x is not equal to y, probability that f of x equal to f of y is pretty low. Okay, so what does it low means? So, I am going to say it is at most 1 over cardinality of f. Okay, is it 1 over cardinality of f? I think so. Yeah, we'll figure it out. Yes, it is. So, what I am saying is, okay, what is this probability over? I mean, the moment I say probability, you should ask me what is the random experiment you are doing, right. So, what is the experiment I am doing? That I pick a random function h from f or f. Yeah. So, I want to say that the number of functions. So, another way to interpret this is that you give me an x and y which are not equal. In this family, the number of functions which will map both x and y to the same location is at most 1 out of the number of functions in this family. Okay. Is it 1 over cardinality we have? I am not.
Because you want to be distributed across the table. So maybe you want 1 by.
No, that's the uniformity thing. So that what you are looking for is, if you are given x and a y in T, what is the probability that h of x equal to y? Okay, or x will be thrown uniformly into any of the locations equally likely. That's not what you are talking about here. I am talking about collisions. Okay, so maybe I think it's 1 over T. You are right. Okay, okay. For a different reason, we will see. Yeah. Yeah. Okay. So I'll come back and repeat this. So another way to think about it is, yes, f of x is a particular location in the table uniformly. So it's 1 over T as the probability. F of y will also get mapped to that location as the probability 1 over T. So the product is 1 over T square for any particular location, right. So now add over all the locations, it's 1 over T. Okay, so for any particular, so this is too universal. Pairwise, we will come to pairwise independence. That is one of the things I am going to talk about, and it just says that f of x to one location, f of y to another the same or another location is the product of these probabilities. Okay, let us not get confused about it. This is what I want. Okay, so what this says is that among this family of functions, the number of functions that will map x and y to the same location is at most 1 over T fraction of the functions. Yeah. Right. 1 over T fraction of this. So this is a definition anyway. So why bother? I mean, I'm going to define it this way, and then we will see the use of this definition. That I'm going to call this. So it has this the property A is what is spelt out now, the small probability of collisions. That's what I mean here, right. So if I pick so basically if I want a good function h, what I will do is if you give me such a hash family, I'll pick a random function from this family, and that has the nice property that probability that any pair of elements get mapped to the same location is at most 1 over T, and this 1 over T is my measure of small probability of collision. Okay. First question. So we're going to, first of all, we have to address a lot of questions here. First of all, is there such a universal hash family? And number two, so what is the use of such a universal hash family? How does it help the space thing which I was talking about earlier, and all of this as we go along. So this is the central family we are going to talk about. Okay, is the definition clear? What is the what? So it's pairwise universal. So this is for I am talking only about the pair of elements that get mapped. Now if you just extend it to more than 2, then that's a different game there. Yeah, the 2 stands for 2 elements that get mapped to the same location. Right, there is a K universal we will come to at the end. Yeah. Okay, so now first of all, is there such a universal hash family, and does it have the other nice properties I wanted, B and C, easy to compute, space to store, H to be small, right. Is there a universal hash family? Yes. Suppose, okay, so let me see. Existence or construction. Okay. So suppose I say all functions from U to T, right. Suppose I just take the family of all functions from the set U to set T. How many functions are there? Can somebody tell me? Right. So, I have this U and T. Let us say I just pick all functions from U to T. How many functions are there? Because U is of size P and T is of size T. T power P, yeah. P power T, okay, let us write. So, T power P, P power T, any other answers? And then we will see which one is. But I am impressed at least that you guys got this, one of the two, which is so. So, why is it T power? Any, yeah. Yeah, so it's P power T or T power P? T power P, right? Each element of the universe has any of the T choices to, because I am not saying 1, 1 on 2 and all that. That is another interesting question you can think about. Number of functions. How do I specify this function? I just have to give the image of every element in the universe, then the function is specified. Okay. So, there are P elements, and if you tell me the image of each of these elements, you have specified the function. There are T choices for each image. Okay. So, that is T power P is the number of functions. Okay. So, now if you just talk about my C, the space to store H, how much space does it, if I have to just store this function H from this family, how much space does it store, does it take? Well, it is P log T, right. Any function is like P log T bits. That's really large. That's a no. Okay. I mean, I will also argue that that's a universal hash function. I haven't done that. Let me do that first. But so if I ask you, is there a universal hash family? Yes, there is one, which is a set of all functions. But I'll quickly tell you why it's universal. That's not very hard to check. Once I tell you that, then the space is too much. Anything, P is my universe size, and anything which is like proportional to the universe size is too much. I can't afford that. So, that is why it is a universal hash family, but not good enough for me. Okay. Why is it universal? Let us go back to the definition and see what is, again I already sort of walked through. What is the probability that f of x equal to f of y if I pick a random function from this family? So, again probability that f of x equal to f of y equal to some one particular element k, let us see, right. We are talking about all functions. So, f of x has how many choices? If you pick a random function, it has t choices. So, it is going to map to k with probability 1 over t. Similarly, f of y is going to map to k with probability 1 over t, and these are all independent. Okay. So, it is going to be 1 over t square, and so there are t choices for k, and you do some linearity of expectations, and then you will see that probability f of x equal to f of y is equal to summation k going from 0 to t minus 1, 1 over t square. So, this is 1 over t, okay, because what is inside the sum is independent of k anyway. So, there is a so all functions is a universal hash family. That is good enough in terms of being universal, but it is not good in terms of space. Okay. So, what I am going to argue is that there is a small sized universal hash family, 2 universal hash family. That's very good. That's also easy to compute. It requires a bit of number theory and modular arithmetic, nothing much, and it's easy to compute. Small space, small size, universe, all the nice properties I wanted. So that's going to be what we'll spend the next few minutes talking about. Questions? Okay. Yeah.
How did they know that this universal hash function, hash family exists? Is there any condition you have to predict?
No, I just gave you this family. Family of all functions is one family which is universal.
Okay, sir, but first you asked, right, how we have to check whether the family exists or not.
Yes, and that question was in the previous slide, and I answered it in this slide. Okay, because I said this is universal. So this family is universal because it has this property, whatever I have written down in red. The only thing is it is too large a family, so it takes too much space to store it. Okay, so now I am going to give you another family which is small sized, easy to compute, and all the nice properties you want. Okay, and that family is not very hard. So now I will tell you why I called my universe as size is p. Any guesses? Why did I call the size of the universe to be p? I am going to assume it is a prime number. Okay. So okay. Now you should question me, what? Universe is user defined. How can you assume something about it, right? Right? So universe is some n elements are given where I have to define my function. How can I assume it's a prime? Who can answer this? So what I will do is I will extend it to the next prime, and I am going to define it over larger set of elements. Okay, you don't want it, that's fine. I want it. So I am going to define my universe to not just your n elements, up to the next. Somehow assuming prime is good for me, it has some nice properties. So I will extend it to my next possible prime, and I am going to define my function on that. But again, now you should ask me, oh, the n has become very large now. Can it be very large? Thankfully, we know there exists a prime between n and 2n for any n. Okay. So it is not very large, it might become, at best or at worst it might become 2n, that is all. Okay. So this is useful. So my universe is now, size is a prime number. So here is my family. What is my family? I am going to define this family is equal to h a comma, it is indexed by 2 numbers a and b. A, B. Yeah, so it is in this ZP star, as they say, or ZP 0 to p minus 1, except I do not want A to be 0, B can be anything between 0 and p minus 1. So that is my family. Well, what is HAB? I will define HAB. It takes an element x from the universe and it just simply does Ax plus B mod P. Okay. So think of it as some sort of a permutation it is doing. It takes an x, it multiplies by A adds B and does a mod P, not good enough. I need to do something more. Why? What is the range? So, what is the range of this function? What is the range I want? 0 to t minus 1. So, what do? I do a mod t. Okay. So, any element x from the universe comes. So, all I need to, okay. So, ax plus b mod p mod t, that is all, that is the function, family of functions. How many functions are there in this family? P square or a little less, because a is not allowed to be 0, right. So, p into p minus 1. Okay. Contrast this with the size of this family, which is t power p, right. So, we said all functions, it is 2 universal, but it is too large a family, t power p, and storing that is p log t base, that is too much. But I am going to give you another family which has only about p square elements, and so space to store is like 2 log p bits. And now I will argue, again it is not at all hard, that this is good enough, this is 2 universal. So, it has all the, and it is easy to compute, look at the function, right. All I need to remember is a and b, it is just one multiplication, one addition and 2 modulus computation. So, it is easy to compute, small space. Now, I have to prove to you that it is 2 universal. Okay. So, in some sense it is a small size family which has the power of all functions. So, as if you are picking a random function from a set of all functions, it has a power in terms of this probability of collisions to be small. Okay. So, now the claim I want to prove, that this family F is 2 universal. And remember what that means, what do I have to show? I.e. for all x comma y in the universe, x not equal to y, probability that a random function, and let us say f is picked uniformly at random from this family, then probability that f of x is equal to f of y is at most 1 over t. That is what I want to show. In other words, a number of functions in this family which will collide a pair of unequal elements is at most 1 over t. Okay. So, it has the power of the family of all functions, but the family size is very small. Okay. So, let us so f, what is, if I have to know f, what is, what do I need to know? Look at this family definition. A random function from this family is means what? A random, B random, that is all. Right? That is another thing. Again, we are going to see later on other lectures where we will say pick a random hash function. Okay. That looks like a very strange statement. How do I pick a random hash function? Now it is clean. Oh, I just have to pick these 2 integers at random, right? A from 0 to p minus 1 to p minus 1, b from 0 to p minus 1. Pick them random and you got a random hash function f. Okay. So, we will show that the number of functions. So, pick proof x from the universe okay, let Ax plus b equal to some r, Ay plus b equal to some s. That is, this means that HAB of, no, not quite. Okay. So, I will just, because there is another mod T computation I need to do to get HA of B R. Okay. So, suppose this. Where the F which I randomly picked is this HAB. Okay. So, from R and S, I am trying to see, can I figure out what is A and B? Okay. Okay, this is mod P. In the mod P world, let me do some subtractions. So, what do I get? A into x minus y is equal to R minus S. All, I am doing everything in the mod P computation. So, which means that A equal to x minus y inverse into R minus S. Sorry. Okay, no, what do I want to say? Okay, so suppose R is equal to S. Okay. So, this function mapped x and y to the same element in the mod P world. Okay, not mod T world, we have to check. Of course, they will be true in the mod T world also, but this function mapped x and y to the same location in the mod P world. Suppose R equal to S, what can you say? Well, you have A into x minus y equal to R minus S, which is 0 in the mod P world. So, what can you conclude from here? Okay. 0 to P minus 1 is a field. I have a product of two numbers which give me 0 in a field. So, either A has to be 0 or x has to be equal to y. Okay. This is where I use the fact that P is a prime. So, in a field there are no 0 divisors. So, A has to be 0 or x has to be equal to y, but we know A is not 0 and we know x is not equal to y. So, this is not possible. So, what does that mean? So, contradiction I would say, or not possible as A is not equal to 0 and x is not equal to y. Okay. So, what have I established? I have established, so think of this line 0 to P minus 1 and I picked some A B and and here is an x and here is an y, and I hope this picture helps. So, x gets mapped to somewhere by this HAB, right, Ax plus b mod P. Y gets mapped to somewhere else, and what I argued is that where they get mapped are always distinct. If x and y are distinct, where they get mapped. So, x gets mapped to R, y gets mapped to S, they are distinct. Okay. This is the first observation, that in some sense the A comma B mapping, what it does in the mod P world, it just sort of like a permutation. Because if A and B is random, it somehow randomly changes the value, but they are all distinct. They cannot collide in the mod P world. Of course, there is a mod T that is taken later, we will come to that later, but for now what I have just argued is that pick any function A B, it does not have collisions in the mod P world of any two non-distinct distinct elements. Okay. So, now what do I want to compute? I want to compute this number of this A comma B such that HABX equal to HABY. X and y are distinct. I want to compute the number of functions that map them to the same location, right. That is the for this universal statement I need to show that HABX equal to HABY, the probability is at most small. This is same as saying the number of functions f what do I need to show? This number of these functions is 1 over t times the total number of functions. Okay. So, to compute this probability, I can compute it this way, that just compute how many functions will map x to y, and I argue that 1 over t times the total number of functions. That is what I have to show. Okay. So, what I have shown is that in the mod p world, your x and y are not going to go to the same place, but in the mod t world, of course, they may go to the same place. Okay. So, let us see, this is, so I am going to write this as number of pairs r comma s, r and s are different, but they are same mod t. Okay. I may be confusing, but it's not very difficult thing at all. What I am saying is your x and y in the first round, when you do the mod p computation, let us get mapped to r and s, and I argued that r and s are different. R and S, in fact, as you vary x and y, r and s are going to be some vary in this number line 0 to p minus 1. So, really the number of functions that will map x and y to the same location is the same as number of pairs r comma s, which in the mod t world they are the same. Okay. So, this is what I want to compute. R and S are different, but in the mod t world they are same, because R and S, it so happens that they are HAB of x and HAB of y, but you might as well think that they are some arbitrary pair of numbers which are distinct. Okay. So, now let us compute this. This is very easy to do, right. So, basically R and S in the range 0 to p minus 1. So, let us fix R. Okay. So, again let us go back to this line 0 to p minus 1. When I do a mod t, this is 0 to t minus 1. So, let us break it up into blocks of size t, and suppose my R is here. Okay. Let us fix R. R has p choices, any of the 0 to p minus 1. How many s's are congruent to R mod p? No. Let us be careful. R and S are distinct in the mod p world. How many values of S are congruent to R in the mod t world? Right. So, for example, suppose R happens to be phi mod t, then you look at somebody who is phi mod t here, R and S would be congruent mod t, and somebody who is phi mod t would be congruent to R, congruent to R mod t, and so on and so forth. So, how many such candidates are there? P mod t minus 1. Yeah, somebody else said something. Yeah, P by t, 1 in each of these blocks, right. If somebody R is congruent to phi mod t, then the phi mod t element here, so think of this as 0 to t minus 1, 0 to t minus 1, 0 to t minus 1. So, that whatever that element in the p line, that element would be congruent to R in the mod t world. So, there is 1 in each of this block which would be congruent to R.